Hi everyone. So let us now discuss the second law of thermodynamics. So in previous chapter, energy is a conserved property and no process is known to have taken place in violation of the first law of thermodynamics. So therefore, it is reasonable to conclude that a process must satisfy the first law to occur. So in this chapter, we have uh, to talk about this second law of thermodynamics. So in which uh, we can include uh, the first law of thermodynamics. So in this chapter, we introduce the second law of thermodynamics, which asserts that process occur in a certain direction and that energy has quality as well as quantity. So as I said that ato i-include ri ang first law of thermodynamics. So sa kuan um, the second law focuses on how we preserve the quality of energy as well as the degree of degradation of energy during a process. So sa first law, ang atong gifocus lang is the quantity of the energy. So wata nag-focus kung wata nag-focus sa first law of thermodynamics, wata nag-focus sa iyang quality, which is kanang how much that energy can become a work, so kana or become convert into work, that energy. So as the degree of degradation, so what do you mean degradation of energy? So the more nga naay sa cycle or the process, di man ta kaingon nga ang imuhang usa ka process is kuan kanang irreversible, which means kanang dili siya uh, uh, which means that taga process sa usa ka substance, so naagi mahitabo nga kanang uh, degrade or kanang mugamay ang iyang energy to convert into work. So from this figure, so a process must satisfy both the first and second laws of thermodynamics to proceed. In this process occur in a certain direction and not in the reverse direction. So para ma-clear na to kung unsay gibut pasabot ani kani nga figure, so let us discuss this. So from this image, so kani sa tamang focus. So we know that if this paddle rotating the water inside the vessel, so maka-create siya og work. So kana nga work in a sense that the water can gain sad og heat. So the more nga dako ang gi-create nga work niya sa kani nga paddle, so the more sad nga moinit ang water or nay gain of heat. So ngano man because so in terms of uh, intermolecular activity sa substance or sa kani nga water, so like centrifuge or kinetic molecular, so mo gain gid siya og heat. Okay, so sa kanipod nga kuan figure, so if naay heat daan ang water, so in a sense pod nga dili sad ka uh, convert into transfer of work into this paddle. Okay, So sa kani atong na conclude that dili reverse walay reverse direction mahitabo sa usa ka process. So a process must satisfy both the first and second laws of thermodynamics to proceed, and process occur in a certain direction and not in the reverse direction. So work can always be converted to heat directly and completely, but the reverse is not true. So from this figure in this previous figure, so and other observations, so we can conclude that work can be converted to heat directly and completely, but converting heat to work requires the use of some special device, and these devices are called a heat engine. So this is a typical illustration or diagram for the heat engine. So for the process of the heat engine. So sa ning diagram nag-consist siya og heat source, which means diha ang ginikanan sa imuhang heat, and then your heat engine that it will mao pud niyang mo produce og work or work net in your heat sink. So sa second law of thermodynamics, as I said, that ato ang kuan diri gifokusan is the quality of the energy. So which means ang QN nimo nga gikan sa heat source, so i-receive sa heat engine and iya man na i-create into work. So dili tanang QN is mahimo gyud or ma-convert into work. So nasay mga waste energy, which means this is mao ni ang heat out or your heat rejected. Okay? So heat engine differ considerably from one another, but all can be characterized by the following. So first is they receive heat from high temperature source or your heat source kato dapat high temp to siya. So such as the solar energy, oil furnace, nuclear reactor, or etc. And the second is they convert part of this heat to work, usually in the form of rotating shaft. So diri nga part is mao to inyo ang heat engine. And third is they reject the remaining waste heat to a low temperature sink, the atmosphere or rivers, such as the atmosphere, rivers, or etc. And four is they operate on a cycle. So what do you mean a cycle? A cycle is a thermodynamic cycle occurs when the working fluid of a system experience a number of processes that eventually return the fluid to its initial states. Or a thermodynamic cycle is a series of thermodynamic processes which returns system to its initial state. So work of a cycle. So work, if we create a mathematical form, so work is equal to summation of their heat. Okay. Where work is equivalent to Qn or Q added minus your Q rejected. So as we observe this diagram, so this is important no nga makaibaw ta sa kaning diagram sa kaning heat engine para in order to we can analyze the cycles. So diri, so the work work, so kung kani ato i-consider as a system, your heat engine, so your work is equivalent to in, so this is a positive sign, and then your out is a negative sign. So if you sum up ng Q, so mo itong mahitabo or mo niyang mahitabo sa inyong equation. So work is equals to Qin minus Q out. So for the thermal efficiency, so for heat engine, the desired output is the network output, and the required input is the amount of heat supplied to the working fluid. So then the thermal efficiency of a heat engine can be expressed as thermal efficiency is equals to network output over the total heat input. So, so as I said that sa second law of thermodynamics, ang gifokusan nato is the quality. So sa heat engine, so atong gikuan ani, ang gidetermine nato is ang performance niya, performance as expressed of in terms of percentage. So which is efficiency is equals to work net over the Qn. So it can also be expressed as efficiency is equals to 1 minus Q out over Qn. Since work is equals to Qn minus Q out. So work, we have work, so Qn minus Q out. So ang iyang equation becomes ingani na 1 minus Q out over Qn. So ato lang to i-substitute no ang work niya. So let us move for sample problem. So sample problem number 1. So heat is transferred to a heat engine from a furnace at a rate of 80 megawatts. If the rate of waste heat rejection to a nearby river is 50 megawatts. So determine the net power output in the thermal efficiency for this heat engine. So para ma-analyze na to ang usa ka cycle, so dapat maghimo tag usa diagram for this problem. So we have the heat source. So this furnace is what we call the heat source na to. And for our devices is heat engine, and then for our heat sink, which is the river. So for the furnace, so mo ni ang gikuhaan nato kuan sources of heat, so which your Qn is equivalent to 80 megawatts. Ano? And they receive from the heat engine. So but naay waste nga 50 megawatts nga heat. Okay? So what is the work here for the heat engine? So 80 minus 50. So for the solution, we have the net power output of this heat engine. So power, it is power means that the rate of your work. So work net is equals to QH minus QL. Heat added minus the heat rejected. So work net is equivalent to 80 minus 50. So it's equals to 30 megawatts. Then the thermal efficiency is easily determined to be efficiency is equals to work net over Q out. No, Q in siya. Q in siya. Okay. So Q thermal efficiency is equals to 30 over 80. So the thermal efficiency is equals to 7.5%. So for adding some information that heat engine some reject some heat to a lower temperature. So temperature reservoir. In order to a low temperature reservoir to complete a cycle. This limitation on the thermal efficiency of heat engines forms the basis from Kelvin Planck statement of the second law of thermodynamics. So, ato na i-discuss later kung saan ang state ni Kelvin Planck. So, the second law of thermodynamics for Kelvin Planck statement. So, it is impossible for any device that operates on a cycle to receive heat from a single reservoir and produce a net amount of work. So from here, this statement, so, so we can conclude this diagram nga atong pakita. So for the cycle, there's no such thing nga have a perfect cycle. So kung perfect cycle ang imuhang kani this diagram, so ingani ang mahitabo sa imong diagram. So walay si pangani walay kanang heat sink. Okay, so kay tanang kuan nimo heat added nimo kay na convert man into kuan work. So kani nga kuan kani nga diagram is this heat engine that violates the Kelvin Planck statement of the second law. So kani ni kani siya violate ni siya sa ato ang second law of thermodynamics. Okay? So for the perpetual motion machine, so we have repeatedly stated that a process cannot take place unless it satisfies both the first and second law, second laws of thermodynamics. So any device that violates either law is called a perpetual motion machine. So if you have kuan, if you have kung nabay existing nga kuan kanang perfect cycle, so napoy existing nga perpetual motion machine. So this is a perfect nga machine, no? So a device that violates the first law of thermodynamics by creating energy is called a perpetual motion machine of the first kind. But in a device that violates the second law of thermodynamics is called a perpetual motion machine of the second. So kani nga kuan, so kani nga machine is wala pa ni nag-exist, no? But this has not stopped inventors from trying to create new ones. So sila sige og kanang research for this kung unsaon nila nga maka-create sila og ing-ani nga machine, a perfect machine. So reversible and irreversible process. So a reversible process is defined as a process that can be reversed without leaving any trace on the surroundings. That is both the system and the surroundings are returned to their initial states at the end of the reverse process. So, mao to ang sa cycle. No? Sa cycle, mo return siya into ang iyang substance is mo return into their initial state. So, this is possible only if the net heat and network exchange between the systems and the surrounding is zero for the combined original and reverse process. Just like sa steam power plant na to, So ang iyang cycle ana is in terms of reversible. So mo return. So naay cycle. So in terms of reversible process. Process that are not reversible are called irreversible process. So like for example, so for this irreversible process, so if you have a cup, one cup of tea are placed in the table, so we can see that ang kanang ang kanang cup of tea nimo is exposed uh, into atmosphere or environment. So which means naa sila kanang uh, na sila transfer of heat. So from your tea, your coffee ba? So mo transfer siya sa surroundings, ang heat niya mo transfer sa surroundings, so which means that their temperature becomes their temperature becomes kanang equilibrium. So at that time, so ang iyahang coffee is dili na mo balik sa iyahang state or pagkainit to niya kay ni kuha naman siya na may equilibrium sa bali sa iyang environment and between the environment and your coffee. For the Carnot cycle is the most efficient cycle conceivable. So there are other ideal cycle as efficient as the Carnot cycle, but none more so. Such a perfect cycle from a standard of comparison for actual engine and actual cycle, and also for other less efficient ideal cycles. So kaning Carnot cycle is only kuan na ni siya idealistic nga cycle, no, which means kanang mo ni dapat ipa-attain sa usa ka actual engine nato. So unless kung naay ang imuhang process is very infinitesimal or very large of time nga makadu of process, so kanang nga time is kuan man, kanang nga process is dili man ka create o kanang friction between that substance. So kana is dili nimo walay kanang kinetic loss or kinetic energy loss nga mahitabo. So ang imong cycle ana is a perfect cycle. So mo na nga the Carnot cycle. So why mahitabo nga ana ang imong engine, no? So this Carnot cycle is for comparison purpose only. So let us have this figure, no? So assume that inside this vessel have a gases or some substance are placing this kanang cylinder head. So from this point 1, so if you kanang move this, so ari nga from process 1 to 2 is your na siya kanang saan siya constant temperature from process 1 to 2. So from process 2 to 3, so gi-exhaust na nimo, which means kung na explosion nga nahitabo diri, so gi-exhaust na niya from here to from process 2 to 3, which means this is a isentropic process. So entropy is equals to constant. So kana. So from adding information, so your cycle is kuan sad ganang combining process, no. So from 2 to 3 we have this. So as we kuan observe that naay kanang isentropic process, napoy kanang constant temperature nga process. So from 2 to 3 we have uh, constant entropy or isentropic process. But from 3 to 4, so we have this, gikuan na ni siya, ang pressure ani is ni dako ni kuan na ni increase na. So from 3 to 4 we have constant temperature. And then from 4 to 1, so from 4 to 1 is mo na ang S is equals to C. Okay? So from 1 to 3 nga kuan kanang volume is what we call is volume displacement. So for the analysis for Farmer cycle, we have this PV diagram. We have process 1 to 2, 2 to 3, 3 to 4, and 4 to 1. So kung atong kuan, this is alternate solution for your work. So pwede sad siya ang work nimo ito ba work nimo is in terms of mathematical for work is equals to in terms of heat Qn minus Q out. Pero pwede sa in terms of summation of work. So this from process 1 to 2 is kuan man ni siya kanang constant temperature. So for the constant temperature we have this P1 B1 L1 B2 over B1. So from here listen from process 2 to 3 we have this for isentropic process. We have P3 B3 minus P2 B2 over 1 minus Q. So kaning mga work ato na ning na-discuss earlier in the previous chapter. So mao na nga nag-una ta og kanang discuss atong mga processes usa ta discuss for the cycle kay magamit man siya para sa atong cycle. So from 3 to 4, we have this P3, V3, and V4, or V3. And for process 4 to 1, we have isentropic process. We have P1, V1 minus P4, V4 over 1 minus T. So for this diagram, temperature entropy diagram, so we have this figure for the Carnot cycle. So we can say that your 3 to 4 kuan length is difference between the entropy of your point 2 or 3 minus the entropy of your point 1 and 4. And for the length of this, for the length for this 1 to 4 or 2 to 3, so we have T2 minus T1 or what's siya? T2 minus T1. No. T2, sorry, T2 minus T1. So for the QA, so for the work is this is the area under this kaning figure mo na imuhang work, the area of the rectangle. So for the work we have QA T1 temperature 1 times S2 minus is 1. So kani nga kuan, kani nga area kani siya is mao na ang imuhang Q added or heat added. And for the Q rejected nimo, mag-analyze tayo sa kani nga diagram. So from here kani nga part kani nga area times S4 minus S3. Okay. Or S2 minus S1. So, kung kuha na tayo ang work, so work is equals to QA minus QR. So, we have T1 times S2 minus S1 minus T3 times S4. Ano, S3 minus S4 ni siya. S3 minus S4. Okay? Where S3 minus S4 is equivalent to S2 minus S1. So, pareha ra sila. Pareha ra silang value for the S2 minus S1. So, T1 minus T3 times S2 minus S1. Okay. Where our efficiency is equivalent to work over QA, where work is equals to QA minus QR over the QA. So for the mean effective pressure or MEP, so we have this PM is equal to work over the volume displacement. So volume displacement or displacement volume, the volume split by the piston in one stroke. So for the main effective pressure is the average constant pressure that acting through one stroke will do on the piston the network of a single cycle. So kung ato ni kuan, observe this PV diagram. So your volume displacement in here is from your 3 or this is a kuan kana maximum expansion per your piston and from here is the end of your kana compression at point 1. So kani kung ato i-minus from 3 to 1 is mo na inyong volume displacement. So for the ratio of expansion ratio or rate and ratio of compression, so we have expansion ratio or all of overall of ratio, expansion ratio is equals to volume at the end of expansion over the volume at the beginning of expansion. So as we observe this PV diagram, we have uh, expansion, volume at the end of expansion, and volume at the beginning of expansion. So sa the end of expansion niya is uh, we have 0.3. And for the beginning of expansion, we have this 0.1. So for the isothermal expansion ratio, we have B2 over B1. So katong 0.1 to 2 is your constant temperature. So isothermal expansion ratio is equivalent to V2 over V1. For the isentropic expansion ratio, we have V3 over V2. So from your uh, from your 2 to 3 nga process is your isentropic process. So mo na nga V3 over V2 ang ato kinahanglanon na volume. So overall expansion ratio is equivalent to V3 over V1. So for the compression ratio is equals to the volume at the beginning of compression all over the volume at the end of compression. So from the volume at the beginning of compression is mao to inyong uh, point 3, and your volume at the end of compression is mao to inyong point 1. So isothermal compression ratio we have is V3 over V4. So from 3 to 4 nga process is kuan man kanang isothermal process man. So atong gamiton nga volume is from point 3 to 4. So V3 over V4. So for the isentropic ratio, or we can say RK, is equals to V4 over V1. From 4 to 1 nga process is your isentropic process. So atong gamiton nga volume is in terms of point 4 and point 1. So for the overall compression ratio, so here, so kaning nga statement, so ang inyong volume at the beginning of compression is at point 3 man, so point 3 atong gamiton, volume 3 atong gamiton. For the volume at the end of compression is mao to inyong point 1, so volume 1 po atong gamiton. So the overall compression ratio is equal to overall expansion ratio. So that's all for now, and thank you for listening.